Greetings, everybody. This is our video solution to problem 3 from Superquiz 3. We move on to our problems about polynomial rings, and we're always going to be dealing here with polynomial rings over a field. Let's read this problem carefully. Okay, we start with our field big F, and we choose two polynomials, little f and little g, in the polynomial ring fx. And we have an extra condition that when we apply the Euclidean algorithm to f and g, the last non-zero remainder equals 4. So first, of course, we can apply the Euclidean algorithm. So this was something we stated in class about the polynomial ring over a field. And the important bit here is that the last non-zero remainder of the Euclidean algorithm, right? This works just like the integers in that it's going to give us, well, something, greatest common divisor. Okay, the only real difference here is that when you're working over the integers, you obtain the greatest common divisor. But when we're working over a polynomial ring, there is not the greatest common divisor. There are only greatest common divisors. Okay, so there can be plural. So the last non-zero remainder of the Euclidean algorithm is a GCD of f and g. Okay, this is very important. So let's go back to the definition quickly, right? What does it mean to be a GCD of f and g? So if you had some u, okay, this is going to be a polynomial, right? This is a GCD of f and g if, so first, u should divide f and u should divide g. Okay, it should be a common divisor. Next, we need to somehow get that greatest common divisor, right, into the game. So the way we do that is by, instead of looking at greatest degree, or if we were in the integers, right, we'd say which one is bigger than the other. We're going to use divisibility, right? We say, so if v is any other common divisor, okay, so v is a polynomial such that v divides f and v divides g, then v divides u. Okay, so this divisibility is what's making u somehow the biggest. Okay. Now, we can make things tighter if we put an extra condition on the GCD, namely that it needs to be a monic polynomial. All right, that's going to take care of the issue, but we're not going to assume that like in this definition of GCD, because, well, that's just not how we've done things, right? And we want our GCD definition to match the definition we've been using for arbitrary commutative rings. Okay, so this is our definition of a GCD, and the important thing here now is that if U is a GCD of F and G, and if, let's say alpha is some element of the field which is non-zero. Okay, so I don't want a zero element because, well, 0 isn't invertible, and I'm going to need that alpha is invertible here. So if alpha is some non-zero element in the field, then I claim alpha times u is a GCD of f and g. Okay. So to show this, we just need to verify these axioms here, right? Namely, okay, alpha u will have to divide f, alpha u will have to divide g, and if we have any other divisor of f and g, then it's going to have to divide alpha u. Right? But this is going to come easily from our definition of divisibility. So for example, we know that u divides f. And so that implies that there exists some polynomial, let's just call it s, such that us is equal to f. Okay, but what if I take u alpha, or alpha u? What can I multiply that by and get f? Well, what if I just took alpha inverse, which exists, okay, so this exists since F is a field. So we have invertibility. And then I multiply by S. Okay, so by the commutativity, I can put the alpha and the alpha inverse together, and they're going to go away. This will just be US again, which is equal to F. So this implies that alpha U divides F. Okay, so similarly, alpha U divides G. Okay, now what about the second condition, right? Making alpha U into a greatest common divisor. So if V is a polynomial such that V divides F and V divides G, then we already know, because we know that U is a GCD, then V divides U. Okay, all right, so i.e. there exists some polynomial T in Fx such that V times T is equal to U. And now we play a similar game. We want to get V times something is equal to alpha U. But that's easy enough. V times alpha T is going to equal alpha U. We just multiply both sides by alpha. Therefore, we conclude that V divides alpha U. Okay, so this tells us that any constant multiple of a GCD, right, other than the zero multiple, any non-zero constant multiple of a GCD is again a GCD. So now let's go back to the question. We found out, right, that the last non-zero remainder, which is a GCD, is equal to 4. But what we just proved is that every constant, other than 0, multiple of 4 will also be a GCD. Now, what does clever Carl say? He says, well, 4 is bigger than 1, and so F and G are not relatively prime. But 4 is a GCD, implies 4 times any constant, so how about we multiply by 4 inverse, which is equal to 1. This is a GCD. So 1 is a GCD, right? In fact, what's going on here is that 1 and 4, they're all invertible elements, all right? These are units not only in the field, but even in the polynomial ring, all right? And so the real moral here is that F and G are relatively prime. What did that even mean? They're relatively prime if and only if every GCD of F and G is a unit. Now, this every is not as strong as it seems. We already know that if you have a GCD, which is a unit, then you get another GCD by multiplying by any constant. So you can get all the units in F, right, by doing that. On the other hand, if you had a non-unit as your GCD, right, so it's not going to be the 0, all right, so if you have some non-unit, it means it's going to be a polynomial of degree at least 1. But now, if I had some other GCD which was a unit, right, so in fact, let's write this down. So let's assume, let's call it H is a GCD, and the degree of H is at least 1. And let's also assume I have some unit as a GCD. And how about we'll call it C, right? In F is a GCD. Okay, so of course C is not going to be 0. Well, because we know that H and C are both GCDs, we know that they divide each other. Right? So this implies C divides H and H divides C. Now let's use the second one, because this feels a little weird. Okay? So this implies that there exists some polynomial, let's call it q in fx, such that h times q is equal to c. Now, because f is a field, we know that fx is an integral domain, which means we can use the degree formula. So if I take the degree of h times q, of course we know this is the degree of c, which is 0, but this is equal to the degree of h plus the degree of q. And h has degree at least 1. So this is at least as big as 1 plus the degree of q. And the degree of q is going to be something at least 0. So this is at least 1. So we have 1 is less than or equal to 0. All right, that would be a contradiction. So if you have a non-unit GCD, then you cannot also have a unit GCD. All right, so relative primeness for polynomials is equivalent to their GCD being a unit. Okay, so this is again working over fx. And a unit in fx just means a non-zero element of f. Right? So if and only if every non-zero element of f, big F, is a GCD of f and g. So clever Carl was, on the right track for the integers, okay, but not on the right track for fx because we don't have a unique GCD. We have lots and lots of GCDs. In fact, we get one for every non-zero element in the field.